Hello, this is Dr. Hanaa Assil, and this is a part of the organic chemistry for the A2 chemistry syllabus. This is on aldehydes and ketones. So let us talk about aldehydes and ketones. These are carbonyl compounds. If we're trying to name them, all the names of aldehydes end with al, like the one that has one carbon, that's methanal, ethanal, propanal, butanal. The functional group, of course, is always at the end, and it is a C, single bond H, double bond O. So these are aldehydes. Ketones end with -one, propanone, butanone, pentanone, pentanone, 2-pentanone. If the C double bond O is on carbon number 2, C double bond O on carbon number 3, that's 3-pentanone, and so on. So the functional group of a ketone is in the middle of the chain. It is made up of a C double bond O that is bonded to two groups, which we call two alkyl groups, or methyl or ethyl, and so on. Aldehydes and ketones. If we look at the structure of an aldehyde and a ketone, aldehyde, we said, has a CHO at the end. Ketone has a C double bond O in the middle. So both of them have the C double bond O, which is a polar part of the molecule, and this causes the aldehydes and ketones to have higher boiling point than the corresponding alkanes. Remember that these would have dipole-dipole interactions in the aldehyde and ketones, so this will have higher boiling point than an alkane that only has the weak van der Waals forces between its molecules. Also, aldehydes and ketones will not form hydrogen bonds with each other. So an aldehyde cannot form hydrogen bond with another molecule of its own. Ketones will not form intermolecular hydrogen bonds, so their boiling point compared to an alcohol would be lower. Remember that alcohols have OH and they can form hydrogen bonds between each other, between their molecules. So the boiling point of an alcohol would be higher than that of an aldehyde and ketone because of the intermolecular hydrogen bonding. But if we try to dissolve them in water, aldehydes and ketones will dissolve in water, since the polar C double bond O will form hydrogen bond with water. It cannot form hydrogen bond with another molecule like itself, but it will form hydrogen bonding with water, so it will dissolve in water. So let's look at this question. Ethanol and propane. What is ethanol? Ethanol is the aldehyde that has two carbons. Propane is the alkane with three carbons. Now he's saying they both have the same molecular mass, but ethanol has a much higher boiling temperature. We said aldehydes will have higher boiling points than an alkane. Why? Because it has what? It doesn't form hydrogen bonds with itself, but it will form permanent dipole-dipole interactions. Now, ethanol, we said, is fully miscible in water. Again, why does it dissolve in water? Because it has hydrogen bonds with water, or it can form hydrogen bonds with water. Propanone, what is propanone again? That's propanone. Has a much higher boiling temperature than butane. Now, we said, why is it that a ketone will have higher boiling point than an alkane? Again, because propanone has permanent dipole-dipole interactions between its molecules, while butane will have only the weak van der Waals forces, so propanone has higher boiling point. Remember, propanone does not form hydrogen bond between its molecules, so B is wrong. Propanone does not have, it's not because it has stronger London forces between its molecules. And it's not because the carbon-oxygen double bond in propanone is very strong. That has nothing to do with boiling point. Another question, some of the physical properties of aldehydes and ketones can be explained by the fact that they what? Never form hydrogen bonds? No, we don't say they never form hydrogen bonds. We said they form hydrogen bonds with water, but not with each other. Okay, they form hydrogen bonds in the liquid state, but not in the aqueous state. Remember, liquid state means when I melt them. No, they don't form hydrogen bonds with each other. They form hydrogen bonds with water. So we said they form hydrogen bonds in aqueous solutions, but not in liquid state. That means not with each other. Okay, tests for aldehydes and ketones. Remember, if I want to distinguish an aldehyde or a ketone from anything else, I use 2,4-dinitrophenylhydrazine. So both aldehydes and ketones will react with 2,4-dinitrophenylhydrazine to give an orange-yellow precipitate. Both aldehydes and ketones form an orange-yellow precipitate with 2,4-dinitrophenylhydrazine. So I use this test to distinguish between aldehydes and ketones and something else, like alcohols or alkanes and things like that. Then to distinguish between aldehydes and ketones, we use Tollens reagent. So this is one of them, because only aldehydes react with Tollens reagent. Tollens reagent is actually a sort of complex between silver and ammonia. When you react it with aldehydes, it gives silver, and the silver precipitates on the sides of the test tube. So we say this is a silver mirror. And remember, only aldehydes will react with Tollens reagent to form a silver mirror. Again, only aldehydes react with Benedict solution. You remember what is Benedict solution or Fehling solution, which is actually a copper sulfate solution. When the aldehydes react with copper sulfate, which is blue, it turns it to brick red precipitate. This is because aldehydes will reduce the copper 2 to copper 1. So it changes copper 2 sulfate, which is blue, to copper 1 oxide, which is a brick red precipitate. Okay, let's take a look at this question. An unknown aldehyde may be identified by measuring the melting temperature of the precipitate formed in its reaction with what? So aldehydes will react with which of these to give a precipitate? Remember, we said it gives a precipitate with 2,4-dinitrophenylhydrazine. It doesn't give a precipitate with Fehling. With Tollens, it gives a silver mirror. And remember, potassium dichromate and sulfuric acid, this is an oxidizing agent, and it will oxidize the aldehyde to an acid, so it doesn't give a precipitate. Again, this question says, when ethanol, remember ethanol is an aldehyde, is warmed with either Fehling solution or Benedict solution, a red precipitate is formed. What are the red precipitate and the organic product? We said when you react an aldehyde with Fehling or Benedict, which is copper sulfate, it will reduce the copper 2 to what? To form copper 1 oxide. And actually the organic product formed would be the sodium salt of the aldehydes, or actually it will be the sodium salt of an acid form. So this is sodium ethanoate. Which test is used to distinguish between aldehydes and ketones? Again, which test aldehydes will react and not ketones? Remember, it is Fehling or Benedict solution, which will give a brick red precipitate with aldehydes only. Which test results in an orange-yellow precipitate with this? What is this? Can you see that this is propanone? So it's a ketone. So which one gives orange-yellow precipitate with a ketone? We said both aldehydes and ketones react with 2,4-dinitrophenylhydrazine. This ketone will not react with Fehling's or Benedict's. It will not react actually with sodium carbonate. We will talk about the reaction of iodine and alkali in a minute, but remember that both aldehydes and ketones will give orange-yellow precipitate with 2,4-dinitrophenyl hydrazine. How many structural isomers with molecular formula this react with Tollens reagent? First of all, we said which ones will react with Tollens reagent? It has to be an aldehyde. So he's asking how many aldehydes will have this formula. So let's start drawing the different aldehydes with 5 carbons. This is one aldehyde with 5 carbon. This is another aldehyde if it is 4 and it has a branch. This is another aldehyde if the branch is on a different carbon. This is another aldehyde when you have the 3 carbons and then 2 methyl groups as branches. So this gives us 4 different isomers that can react with Tollens because they are all aldehydes. This question refers to the following molecules, all of which have a carbonyl group. And he says a brick red precipitate is formed on warming blue Benedict's or Fehling's with what? Again, Benedict's or Fehling's will react with aldehydes. So he's basically asking which of these are aldehydes. Remember that these two are aldehydes, the others are actually ketones, so only W and X will react with Benedict or Fehling. Again, butanone can be distinguished from butanoic acid by the addition of what? This is a ketone, and I'm trying to distinguish it from an acid. So which one will this react with? Remember, we said ketones will react with 2,4-dinitrophenyl hydrazine. They don't react with Fehling or with Tollens. So this would be the one that will distinguish the butanone, the ketone, from the acid. Which correctly shows the reactions of ethanol. This is ethanol. Propanone. Remember, keep all of these in mind. What is he talking about? So he's saying which of these will react with Tollens? Remember, ethanol is an aldehyde, so it will react with Tollens. Which of them will react with 2,4-dinitrophenyl hydrazine? Well, both aldehydes and ketone. So both ethanol and propanone will react with 2,4-dinitrophenyl hydrazine. Again, a compound X with molecular formula this gave an orange precipitate with 2,4-dinitrophenyl hydrazine. What does that tell you? If it gives an orange precipitate with 2,4-dinitrophenyl hydrazine, that means it is either aldehyde or ketone. Then it also gave a silver mirror with Tollens. That means it's what? It's an aldehyde. So which of these could not be X? So the question is, which of these is not an aldehyde? So that would be D. The others are all aldehydes. Sucrose can be hydrolyzed by warming with dilute hydrochloric acid. Remember that sucrose is actually an aldehyde because it has the CHO group at the top. State what change you would expect to see when glucose is boiled with Benedict's or Fehling's. So this is actually an aldehyde. I'm reacting it with Benedict's or Fehling's. It will reduce the C2 to C1. So the blue copper sulfate solution turns into the brick red precipitate, which is copper 1. He's asking you to explain the chemistry involved. That means you need to mention that the aldehyde is a reducing agent. It reduces the copper 2 in Benedict or Fehling to copper 1. That's why you get a brick red precipitate. Okay, how do we prepare aldehydes and ketones? Well, one method of getting an aldehyde or a ketone is oxidation of alcohol. Remember that if I have an alcohol, so let's say I have a primary alcohol, if I add acidified potassium dichromate or acidified potassium manganate, the first thing is the primary alcohol is oxidized to an aldehyde. If I continue to oxidize it, it further oxidizes to acid. So this is one method of getting an aldehyde. So remember, oxidation of a primary alcohol gives aldehyde. But if I'm doing the same to a secondary alcohol, we said in that case I get a ketone. Again, we're doing alcohols with an oxidizing agent, acidified potassium dichromate or acidified potassium manganate. Primary alcohols give aldehydes, secondary alcohols give ketones. Or I can get the aldehyde by reduction of an acid. So if I have an acid, I can react it with lithium aluminium hydride in dry ether. So the reagent is lithium aluminium hydride in dry ether will change the acid to an aldehyde, and further reduction will give an alcohol. This aldehyde is then obtained by reduction of an acid, and the reagent is lithium aluminium hydride in dry ether. Okay, let's take a look at this question. It says ethanol may be prepared by which of these? Okay, let's take a look at the choices. The first one says heating ethanoic acid with lithium aluminium hydride in dry ether. This will actually give ethanol, but it will continue to give ethanol at the end. So this will actually give an alcohol again. Now, if I say refluxing a mixture of bromoethane and sodium hydroxide, well, bromoethane and sodium hydroxide would give me the alcohol, not the aldehyde. Refluxing a mixture of ethanol with acidified potassium dichromate, remember we said we can oxidize a primary alcohol to an aldehyde, but if you heat it under reflux, it goes on to form an acid. It does not stop at the aldehyde. If we say distilling from a mixture of ethanol with acidified potassium dichromate, that is when we get the aldehyde. So as it forms, I distill it out, so it does not continue until it forms acid. So that is my choice. Okay. Reactions of aldehydes and ketones. So if I have an aldehyde or a ketone, if I put a reducing agent like lithium aluminium hydride in dry ether, it will reduce the aldehyde or the ketone to form an alcohol. So this is actually how we get an alcohol from an aldehyde and ketone. Remember, this is lithium aluminium hydride in dry ether. Or I could add hydrogen cyanide. So an aldehyde or a ketone would react with hydrogen cyanide. Hydrogen cyanide is obtained by sodium cyanide in presence of an acid. So this is something that will give a CN and an OH on that carbon. So it's called a cyanohydrin. I can go on to hydrolyze this cyanohydrin, and it will continue to give an acid. So this is actually a method of doing what? This is a method of adding a new carbon on the chain. So this added an extra carbon on the chain. I can also continue to react the product with concentrated sulfuric acid at high temperature, like 180 degrees Celsius, and I end up with the alkene that has an extra carbon from what I started with. Okay, what is the mechanism of the addition? At the carbonyl, the nucleophile attacks at the carbon, the electrons move to the oxygen, so I get an O minus, and this O minus reacts with the acid because this is in presence of acid, and it gives me the cyanohydrin. Okay, did you notice that mechanism? Let's take a look at this question. This question is about reaction of cyanide ions with a ketone, and a student wrote this mechanism. What is the error in this mechanism? Of course, the cyanide will attack the carbonyl, that is correct. But then what is he doing? He's saying the H plus will attack the O minus. No, it is the O minus that will attack the H plus. So the direction of the curly arrow from the hydrogen ion is the wrong part of this mechanism. Which diagram shows the first step of the mechanism of nucleophilic addition of hydrogen cyanide to propanone in presence of potassium cyanide. Okay, so we said the cyanide should attack the carbonyl, and the double bond of the carbonyl electrons will go to the oxygen to form an O minus. So which of these is the correct one? Okay, can you see that A is the correct one? What's wrong with the others? B, he has an arrow going from the double bond to the carbon. That's wrong. It has to go from double bond to the oxygen. Now, what's wrong with C? C has the wrong partial charges on the carbon. The carbon should have a partial positive and the oxygen partial negative. So C is wrong. And D, what's wrong with D? The arrow is going from the carbon to the cyanide. That's wrong. Okay, so reactions of the carbonyls with aqueous iodine, alkaline aqueous iodine. This is called the iodoform test. And this is a test to show the presence of a certain group. If I have a ketone that has CH3CO, I can show that it has this group because it will react with iodine in presence of sodium hydroxide aqueous. So this is alkaline aqueous iodine. And it forms a yellow precipitate. Can you see the yellow precipitate? So formation of a yellow precipitate in the iodoform test shows that I have my ketone, I have a group which is CH3CO. So let's look at this question. A carbonyl compound with molecular formula this reacted with iodine in alkaline solution to give a pale yellow precipitate. That means that it has the CH3CO group. Now, which one has CH3CO? That is this one. So this is the one that will give pale yellow precipitate in the iodoform test. The others don't have this group. When propanone reacts with iodine in presence of sodium hydroxide, the precipitate formed has what formula? Remember, when we have propanone, propanone is CH3CO, CH3. So it does have the CH3CO group, so it will form a yellow precipitate with the aqueous iodine, aqueous alkaline iodine. Now the precipitate has what formula? We said this is the formula of the precipitate that is formed. This question refers to these compounds, and he says a pale yellow precipitate is formed when iodine in alkali reacts with which of these? Again, iodine with alkali will give a yellow precipitate if the compound has what? CH3CO. So which compounds have CH3CO? That's Y and Z. This question is about nucleophilic addition of hydrogen cyanide to butanone. Now, he's saying that the cyanide attacks the carbon and the electrons go to the oxygen. That is correct. So what is the intermediate that is formed? Which one is correct? We said this one is correct, in which the cyanide attacks. So the O now has an O minus. Which statement about the mixture of organic compounds formed is not correct? So which of these is not correct? He's talking about this reaction, of course, and he's saying the organic products of this reaction. Which statement is not correct? If you look at this one, he's saying it will rotate the plane of polarized light. No, we said when the nucleophile attacks on the carbonyl, it can attack either from the front or from the back, and that means a racemic mixture is formed, and the racemic mixture will not have any effect on the plane of polarized light. An organic compound gave a pale yellow precipitate when warmed with iodine sodium hydroxide. What does that mean? It has CH3CO. It also gives steamy fumes when tested with phosphorus pentachloride. You remember which group will give steamy fumes with PCl5? Well, that is an alcohol. So what we're looking for is something that has both a CH3CO and an alcohol, so it is this answer. Okay, thank you for listening. That was about aldehydes and ketones, and in the next videos we will continue talking about organic chemistry. Thank you.